So today, my plan for this video is to literally cover 4 lectures of MIT real analysis, and not entirely 4 lectures, 3 lectures actually, and a bit of the 4th lecture. So I will explain this as I'm only 11. So I think other people could understand this. I'm only 11. Yeah, I know. So, let's say, let me just put the banner. Am I even spelling this properly? It's going to be embarrassing if I... Okay, so it's already writing on that. I don't even want to write on that. Just put 18.100. A. It's the literal random code. So, that's done with. I'm going to delete this slide. Lecture 1, sets, set operations, and mathematical induction. I actually don't put many of the proofs, or I might not even prove so many, because it's a lot of saying. I'm doing this to practice as well. So, purpose of real analysis is to gain experience. So, experience to prove statements. I'm not going to write about the whole thing. So, prove statements. Prove statements about the real numbers, functions, and limits. If you want to look at my Vedic maths videos to understand what the heck limits are. Anyway, that's later on, so if you don't know what limits are, it's fine. And functions basically takes an input and returns an output. If you guys know algebra, function is basically something which takes in a variable x and does something to x to bring out y. So y is going to equal to 2x plus 1. So you just take values of x and you spit out values of y. So then then these are ordered pairs on a coordinate graph. And basically that's a function which would probably look like this. Because it should. So 0 would be 1. So yeah. It's actually fast growing, so this is x. This should be 2x. And then and apparently this is actually 1 over, so here. So this is 2x plus 1. This is x plus 1. So this is the graph 2x plus 1. It even goes down here. If you'd like to continue on. In fact, this descends more. This just stays normal. That's functions for anyone who needs to understand. Because there will be a bit of functions. In fact, a very weird definition of it. So, sets. I will tell you the definition. A set is a collection of objects called elements or members. So it's a collection of objects called elements or members. So the objects are called elements or members. It's a collection of that. This is a very ambiguous definition. Very weird. But we don't want weird definitions, so I'm happy with this. So the empty set is basically empty. There's nothing in it. It's literally empty. So it's denoted by a circle with a dash through it, which you can clearly see. Now, new notation. Let's get some new notation ready. A is an element in S. Oh, sorry, this is not supposed to look like an E. I mean, like, it'd be very creative if it does, but it's not. It's not a ES, it's a curve. It's like a curved E. Yeah. So A is in S. A is an element in S. S, remember, S is it just has elements in it. Like, say, 1, 5. If A was an element in S, A could be 1 or 5. Or if A was an element in S, it could be the empty set. The empty set is always, no, actually no, the empty set's still a set, so no, not an element. We'll get to sets. And if A is not an S, or basically everything else except 1 and 5, very exclusive, A is not an S. Now, in proofs, there's actually in statements, so it'd be very useful to know, and I might not even write the complete proofs down, or I'll just tell you, like, this words, because, well, yeah. But if you were to ever take a real analysis course, it's good to know beforehand. This upside down A means for all. So basically, for all X in S, and is there in this is there exists. There exist N in S such that 2N is a rational number, is a rational. Now this might seem very weird, like, what are you trying to do here? And, well, again, we're referring to the same set S, 1 and 5. So 2N's obviously going to be rational. 5 times 2 is 10, and 1 times 2 is 2. You already don't even need. So, anyway, this is some new terminology. Now, it's actually going to continue. Oh, there's no more. Oh, yeah, there is. Yeah, there's more. So, this is for statements and proofs again. All 4 of the next 2 and the previous 2. This is implies, like if X implies A. Now 6. If and only if. So basically it's 2 statements. And it can happen if and only if. So, if X and only if A, then X implies A like before. Again, this time X and A are just statements, like words, like. So it implies, and A also implies X. So say X is if I can't actually think of any examples right now. Anyway, so right now it's just X implies A, A implies X. I can't really remember definition. A set A is a subset I'll just definition. I'm telling you definition. A set A is a subset of B, or A this would be circular, A stretched out C, or maybe you just do A mini C if A, an element in A, apply B, an element in B. Or, well, this is a bit weird. This is very weird. So, basically, for the third grader, all elements in A are in B. So, this time, the rational, the empty set is always in any set. S is any set. Yes. Two sets are equal, or A equals to B if A is A is in B and B is in A. So if B is in A, if A is in B, then A is a part of B. But if B is in A, then B is a part of A. So the only situation can happen, they must be equal. Simple. Or I think if it's A, or the weird definition relating back to that, this time it wasn't in my notes. So B is in B. Not too hard. A is a proper subset if, so now we use our previous two statements. A is in B, subset of B, but A is not equal to B. Because that makes sense. Like, why would you care about subset? They're equal. So now this time, X is a oh, by the way, here's the proper subset notation. Very weird. I really just don't want to use this. Like, it's just so bad. A is not in B. Like, no. Please no. Like, whoever came up with that, I don't know what they were thinking. I mean, like, I understand, but, like, no. And that makes sense. If you want a subset, you don't want them to equal, it's just subset. So now, this is not a subset of everything. Because it's not proper set of S if S does not equal to the empty set. And this is not just for, oh yeah, but like any, yeah. And set building notations. So basically, we use these brackets and we put elements, or we define a set as elements which are in a different set, or we can just call that A. So like all elements which are in a different set, which follow a specific function. Or they just, or X PX. Simple as that. And yeah, we just talked about functions, so basically you should notes. That's why we talked about it. And now, here are some very important terms. Some very important type of sets. These are just type of sets. Remember that. Very interesting. So, the natural numbers. Very interesting set. It is 1, 2, 3, 4. Onwards to alpha. No, Okay, that was not covered in real analysis, but okay. Natural numbers, infinitely big. Integers. Basically, you could just define it as this. X in natural numbers. This is, I actually didn't put this in my notes, I'm just thinking of this. So then I don't even know how to write this. X, and negative X. Approve both of them. Or we can just say, or we just know the integers is basically, oh, but that doesn't work for 0 and 0. You should include 0. 1, negative 2, 2. Wait, does it include 0 though? Does it include 0? Does the natural numbers include 0? Nope, no 0. Okay. So there's no 0. But this time there is a 0. So we're done with the integers. Z with the weird thing and natural numbers N with the weird thing. All these will have the weird thing. It's pretty cool. This is the rationals. Or over here we got a proper definition. M over N. M. N. In Z. N does not, sorry, it's not. Okay, this time it's an equal sign. Not equal to 0. Sorry if it looks weird. Don't look at the E. So it's basically M divided by N. M and N are both elements in Z, and N does not equal to, yeah, this is supposed to be dot not equal to. So it's basically just fractions and decimals and stuff, and negative numbers. And now finally, actually not finally, actually, yeah, I'll also show you something extra, which is later on in mathematics. How am I going to approach this? So, yeah, just admit it. It's, oh god, how did you draw it so well? How? Okay, I want to see the real number set sign. How did I draw set sign? I'll show you the good one. What? That is not how it looks. R. Teach me that. Oh my god. So you basically take 2 lines and you just draw an R. Okay, I'll just do that, I guess. So this is the R set. Yeah, that's not the best. Oh, okay, that's why. No, that just looks bad. Okay, so R. Real numbers. Now, we can't actually describe this yet, but hey, you guys want to describe it? It's lecture 4, so here's some interesting lecture 4 stuff which you want to understand. We still haven't completely understood it yet. That's our goal. Actually, it's lecture 3. Yeah, we got it in lecture 3. Theorem. There exists a unique ordered field containing the rational numbers with the least upper bound property, which we denote R. That is the definition of the real numbers. Though, you will never understand that. Actually, I'm just joking. You will understand that. You might already understand that. If you are, good job. Because right now, you're not supposed to know that. So, proper definition of real set. And then there's complex numbers, which is much, much easier to draw. It's like square root of -1 is I. Finally. All your childish wonder is gone. Square root of -1 equals to I. And then there's like numbers like 3i plus 5 square root of negative n equals to square root of n I. There's an entire system based on that. Entire operations, but okay. When does this end? This is going to be a bit long, so conclusions. Let's just quickly do this. And Z Q R which is also in complex, but we're not doing that. But anyway, right now focus is R and all of these. So, definition. The union of set A and B is A union B. X. X is in A or X is in B. A union B. A intersection B. It's basically all the elements of A, only once, like each element only once, like no repeats. A intersection B. This is where you take, so basically A union B is A plus B minus A intersection B. Now what is the intersection? Because I didn't actually cover it yet. The intersection is all the same stuff, so you could just take just the same definition, except of the or it's and. So it's X is in A, and X is in B. So that's done with. Intersections, very nice. The set difference of A to B is the set A to B equals to X in A, but X is not in B. X not in B. So it's basically all the elements in A which is not in B, or A minus A intersection B. The complement of A is AC, C on top, which is only X not in A. Only X not in A. All the elements which is not in A is in A complement C. So, in the complement of the rational numbers is the irrational, which doesn't have its own denotation, but if I ever talk about it, I will use this. This is not an official symbol. It is my own deciding. Hopefully it gets a new trend though. I like this. I like this. I like this. Keep it going. Irrational. And, well, for the opposites of the natural numbers is basically, well, yeah, it's X not in natural. You can just say that. It's not that deep. Or, basically, for example, well, it's basically X in natural. X in natural return negative X. So it's this set plus the set encasing 0, because 0 is not in this set. Okay, I gave enough examples. Oh yeah, I was supposed to give these examples. Oh, okay. A and B are disjoint if none of them share the same elements, or for more formally, the intersection is nothing. Like, if they share nothing, they're Well, definitely not joint. So, there's some here are some remarks. A and AC are always disjoint. A for sets. What? For all sets possible. For all sets, there exists a disjoint set. This is just my own thing again. Like, obviously there will be a disjoint set. That could be. What about complex numbers though? Like, what do you think is going to be disjoint with them? Huh? Well, something. Something will have to exist. Maybe the set of the infinite omegas. Like, these are different types of infinity. Okay. Talk about that deep. It's not even real analysis. So, theorem, De Morgan. Some De Morgan's laws. In my original set theory video, which was on a notebook in very bad quality, I only mentioned 2 of these laws. And there's actually entire registered proof, which I'll just say, like literally say it, because this is taking way too much time. Never expected this. I was planning to do 4 lectures. I might not even get to this. I might not even do the sets part of this lecture. Forget about getting through this lecture. So, oh yeah, these were. Oh yeah, these are actually pretty interesting. I'm gonna actually put it down to make it look like divide, even though it's not divide. And if you replace these symbols, if you flip them over, same theorem. In fact, these ones also flipped. So, and his entire proof. So basically, a proof, you assume P, and just Q is true. Actually, what? Okay, I don't know what was that about, but proof. B union, the first law, B union C, the complement of B union C, because B complement intersection C complement. So, let B and C be sets. We want to prove that the complement of B union C is, first we're gonna prove that's a subset of B complement intersection C complement, and we prove B complement intersection C complement is a subset of the complement of B union C. This is way too much for you, right? Okay. So basically, we understand that if this is literally like a statement. So like each of these are statements. So connect these. And since we're trying to prove they're equal, we just prove both sides. What to show? B union complement of B union C. Oh God, well I'm not gonna. The complement of B union C is a subset of B complement intersection C complement. So let X be in complement of B union C. Then X is not in B union C, which implies X is not in B and X is not in C. Because like complements is a complete opposite, like they're always disjoint. Since X is definitely not in B union C. So X is in B union C and X in C union C. We didn't actually have to do that step before. We could just get this. So X is in BC intersection C because it's in both of the sets. Yeah. It's not that deep. Thus, our previous statement. X is obviously going to be in B complement C intersection C complement C if it's in both of them. If it's x is in A and x is in B, x is definitely in A intersection B. This is common logic. This is in A. Yeah, I know this. Oh, intersection. Sorry, intersection. And this is a full X, not one of those other Greek symbols. So, what to show? Now we show the opposite. B complement C, intersection C complement C is in complement of B union C. Let X be in B complement union C complement. Then X is in B complement and X is in C complement. So then X is not in B and X is in C. So then X is not in B union C. So then X is in the complement of B union C. Thus, since both statements, the statement's been proved, and if both statements are equal, if both statements work, then they're equal using our previous shown logic. So, we have finally finished this. We haven't even finished the first lecture. Forget about that. We have induction to do, and oh hail. Oh god. It's a lot. But that's it for today on the it's not even lecture 1 done, but like usually lectures take an hour, so this is actually a pretty good review. It's only been like 30 minutes. So anyway, bye. Again, remember